done in another language. So essentially we have three kind of loops we care about. Doing just a little bit of review. We may as well code them up. We have while loops. We have do loops, which you didn't have in Python. And we have for loops. So your classic loop is your while loop. There's nothing you could do in any of the other loops that you can't do with a while loop. We're doing about 5 minutes of review. Are we on lecture J like I think we are? Yeah, I think we are. Okay. Yeah. I wrote a note to the effect of, where is everybody? I knew you'd come, but where is everybody? It's a holiday. Nobody told me in advance. That's right. All right, our boilerplate seems to keep getting longer and longer, but that's all right. This is lecture J. All right, as soon as we have this quick little review of loops, we're going to go off the beaten track and talk about structures and classes. So we have our three kinds of loops. We have while, for, and do loops. While and for are known as pretest loops because the loops happen first, the tests happen first. Do is a post-test loop. You'll see the difference real fast. Not a post-test lopo, but a post-test loop. So a loop just looks like this. Int x. We can initialize x to something, like x is equal to 1. And then we set up our condition. Here's our test. It's a pretest loop, so the test happens before the body. So while x is less than or equal to 10, then why don't we write out x, see out x, see out greater than less than x, less than the NDO. And then we have to update x, or else it'll just be an infinite loop. It'll keep printing out 1 over and over. So x plus plus. And we'll run it, and we will see, as a matter of fact, it will count from 1 to 10. Go, go, go. All right, here we go. Yo. So here we go. It counted from 1 to 10. It's a pretest loop, meaning that the test happens first before the body is executed, and if this condition is not true, it won't even go in there, just like an if statement. If we set x equal to 100, x is not less than 10. So just like an if, it wouldn't go in here. The same is true of a while. So if I run it now, it's not going to print out any numbers whatsoever. So a for loop is just a fancy way of writing a while loop. Why do we want a fancy way? Well, this loop has 3 pieces. A while loop has 3 elements. 4 if you count the body. 1, you initialize the loop control variable, which I'm going to call LPC, or no, LCV. And then you test the loop control variable. And then after that, you have some kind of body like printing it out. And then 3, you have the update of the loop control variable. And if you don't update the loop control variable, then it is an infinite loop. Like if I commented that out and then ran it. There. Just a whole bunch of ones. Not what we wanted, and that's because if x never changes, this is always true. So if we have to do those 3 steps every time, why not create a syntax that lets us do all 3 of those? Like this. For x equals 1, here's where we're going to start. That's our initialize. And then we're going to test it. Keep running while x is less than or equal to 10. So after the semicolon, I put x less than equal 10. And another semicolon. And then there's an update. Do the third thing. X plus plus. And then inside the body, we could again print out x. Now that's going to do the exact same thing as the one above it. Well, if it's going to do the exact same thing, why do you need it? Because it's nicer syntax, right? We can see at a moment's notice, at just a quick 2-second glance, where it's starting, where it's ending, and what kind of update it is. Whereas if we're going to read this one, it could take a little bit more reading to figure out what it's doing. And whenever I write codes to show students, quite often I leave the update off, and then it's an infinite loop after we compile it and run it, and I have to go back and I have to edit it. And I'm doing that usually half the time, not intentionally. But you never forget to update it if it's right there in the syntax. There's nothing you could do, right? Let's just skip it. All right, so this is another pretest, right? Because if this test isn't true, it's not going to even print x. Like if x is set to 100, just like it was on that while loop, the order in which it does things is it initializes, just like that. It does the test, then it does the body, and then it does the x plus plus. And then it comes back and does the test again. And then the body and the x plus plus and the test and so on. So if this thing's not true, then it doesn't even go into the body. Like that. It didn't print it out a second time. Now I'm going to change that back to a 1. What if we wanted it to count down? We could make it count down. What if we wanted to count down by 20s? Starting from 100 and go to 100, 80, 60, 40, and 20. Well, then I'd just initialize ourselves to 20 and keep running as long as x is greater than or equal to 20. And instead of adding 1 to it each time, we're going to say x minus equals 20. No space between a minus and the equals. Now to print 100, 80, 60, 40. Notice that we had to flip this right, because if I'd left it the way it was, then it wouldn't do anything, because x is starting at 100. It's not less than 20, so it wouldn't print anything. We just had to flip that to make the logic work. And there we go. It printed out 100, 80, 60, 40, and 20. Now, like I said, there's just about nothing you can do with a for loop that you can't do with a while loop. So technically, the language might not even have to have it, but it's a very useful syntax, and so every language does have it. Now here's a syntax that not every language does. Python does not have a do loop. It's a post-test loop. And it looks like this. Let's set our variable equal to something. X is equal to 1. And then we're going to have the word do, followed by a curly brace. And inside the curly braces, we're going to have a body. Cout. Let's make it a little bit more interesting. Do space end quote, arrow, arrow, x, arrow, arrow, endl, just so our output looks a little bit different. And then let's update x, because that's still necessary. But after the closing angle, we need our while clause. This is our post test. Keep running while x is less than or equal to 20. Right? We're going to print out all the numbers between 1 and 20 that way. Now, is there any reason you could not have coded this with a while loop? No, there's no reason you could not have coded this with a while loop. That's why Python didn't even bother. too, because anything you can do with a do loop, you could do with a while loop, but the logic might become a little bit gnarlier if you did not have the do loop syntax. Because it does do one key thing different. Alright, and we see it did from do all at 1 to 20. Now, do you remember when we said that if this condition was false inside of while, it wouldn't even do the body one time? What if the condition is false here? Like, what if we set x equal to 100? Is it going to go into the body of the loop? It sure is, because there's no gatekeeper here. There's no test before the body. So it's going to print something out even though 100 is not less than 20. It performs the body and then it hits the post test. And so since x is now equal to 101 by there, it drops out. It's kind of like a while loop. You're checking somebody's ticket before they go into the theater. And with a do loop, you wait until they get into the theater before you check them. Right? So they're already in the theater. If nobody was outside taking your ticket, you could waltz right in. Well, there's nothing stopping the code from waltzing right in and doing the body of the code. That's the difference between a do loop and a while loop, is that a do loop, the body is guaranteed to be executed at least one time, whereas with a while and a for, it's not. We may as well, that's so important, I'm going to put it as a comment. Use a do loop if the body has to be executed at least one time. And then, when would we use a for loop? Use a for loop if it's a counter-based loop. Otherwise, use a while loop. What do I mean counter? Well, you know, x is starting at 1 and is going to 1,000 or something like that. The for loop syntax is so genericized that you could even use it for indefinite loops, loops other than counters. But in general, if it's a counter-based loop, if you're stepping through a particular series of pieces of data, you may as well use a for loop. And if you get to the point where you can write every kind of while loop with a for loop instead and the syntax looks good, go for it. Technically, if your language supports a for loop the way that C++ and Java do, you could get away with never using a while loop, but that's kind of silly. The while loop syntax is kind of very fundamental. All right, now we're going to go off the map and we're going to talk about structures and classes. What is a structure? It's something that holds multiple pieces of data. Right now, we've only been holding a single piece of data in a variable. We have something called temperature. It holds one temperature. We have something called weight. It holds one weight. We have a variable called x. It holds one integer at a time, or one float, or one string at a time. Well, we can create something that'll hold a whole bunches of pieces of data at one time. Like this, struct emp underscore rec for employee record. So struct emp underscore rec, curly brace on the next line, and every employee has a first name and a last name, and maybe a employee ID. So every employee has a first name, so string f name. Every employee has a last name, so string L name. And every employee has an ID, which we could just make an integer, right? Now, in this particular language, you have to close your structure and class definitions with a semicolon, whereas in Java, you do not. I don't think the semicolon would cause the Java to not compile, but it's not necessary. All right, now we're going to create an employee. emp underscore rec E1 for employee 1. Semicolon. Now let's add some values to it. E1 dot fname is equal to Bob. E1.lname equals Roberts, in quotes, semicolon. And E1's employee number is 123. So E1.lid, E1.id equals 12345. And let's make another employee record. EMP underscore rec E2. And put whatever first name and employee ID, last name and employee ID you want. I'm not going to even read them aloud. You just make them up. E2.name or fname. Four, five, six, seven, eight, whatever, right? So now we have one variable that contains multiple pieces of data, right? It's got a first name and a last name and an ID in it. Same for employee E2. We could write a function that would print out like the person's full name. And we could pass that variable in as an argument to fill a parameter in that function. I'm pausing because I think I typed too quickly, and some people need catch-up time. Let me delete some spaces here. Okay, did not mean to go that far. Right. Okay, so I'm going to go and add a function. Yeah, why don't we just put it underneath all the code? Well, because we're going to need a prototype if we do it here, but that's okay. This function doesn't need to return a value, so we're going to declare it as void. Void space print underscore emp parentheses. And it takes an employee record as an argument. Emp underscore rec space e. Just, you know, that's the employee name. I mean, that's the employee. Or I could give it a better name, like the whole word employee. But it sure is nice just to be able to type E. I'll leave it the word employee. Don't get lazy. Close parentheses. Why are you giving me grief? Declaration is incompatible with print EMP declared on line 80. Well, no kidding. I've just declared it. Why are you complaining about it? Is this one of those that disappears as soon as I compile it? Oh, what do you know? It is a problem. Why? Because I declared my structure inside main. So it is local to main. So it can't be accessed anywhere else. So I need to cut that employee record structure and move it up to the top of the program. Or better yet, in a header file. But I'm going to leave it at the top of the program for now. So I'm scrolling back up and I'm grabbing everything from this line, hitting shift down arrow, up to and including the thing with the curly brace and the semicolon, and I'm cutting it. Don't just copy it because you have to come back and paste it later. I mean delete it later. And scroll up and paste it above main. Now that'll fix the error of the function that we were writing. It just didn't know what an employee record was, so it couldn't go from there. So there we go. Now let's write out the employee. Cout, arrow, arrow, quote, employee name equals space end quote. Now let's write out their first name and their last name. Cout, arrow, arrow, employee.fname, less than, quote, space, quote, less than, employee.lname, semicolon. And then cout less than, quote, space, ID equals, end quote, less than, employee.id, employee.id, less than ENDL. Now, since we put this function at the bottom of the code, it'll compile, but we won't be able to use the function. We haven't called it yet, so it'll compile, hopefully. But it doesn't do anything different because I haven't actually called it. And when I try to call it, I'm going to get an error. So if I go above that system pause, or if you don't have it, above the return, and I call print underscore EMP parentheses E1 in parentheses semicolon, it's going to underline it eventually. Print underscore EMP parentheses E2 in parentheses semicolon. It's not underlining it, but if I compile it and try to run it, it should give me an error. And it did. It says identifier not found. The reason why is this function is not defined above where it is being used. But we can fix that using a function prototype. A function prototype is when you just copy the header of the function and then put a semicolon at the end of it. So I'm going to use my mouse to copy the entire header of the function. Right click and copy it, and I'm going to go right below where we declared the structure and paste it. I'm going to come up here, scroll, and paste it, but just put a semicolon there. So why would you do that? Why did I not just create the function there? Because I might want to put the function in an entirely separate file. And if it's in an entirely separate file, it's the same deal. The code wouldn't know anything about it unless it saw this prototype. So this is a prototype. A prototype is a function declaration without a body. It is used to declare a function so that the code can be compiled even if the function body itself is located elsewhere, like another file. Have we talked about function prototypes yet? Or is this the first time I mentioned it? All right. All right, I may need to slow down and scroll past the code and stuff like that, but let me make sure it runs first. All right, and it printed out employee Bob Roberts, and there's his ID, and it printed out Becky Simpson and her ID. So we had 3 pieces of data that we printed out, even though when we called the functions, we only passed in 1 variable. Right, down here, we only passed in 1 variable. Okay, so these are the changes we made since we had it working previously. We added these 2 print statements, and we added this function. So if you need to pause the recording and type it in, go for it. Alrighty. A class is just a function. Excuse me. A class is just a structure with functions added to it. Except then those functions have a different name. They're called methods. So we'll hold off on that for now. But we could make a class called employee, and we could add some functions like that print function directly inside the class. We'll do that at a later point. Is this working for y'all guys, or do I need to come and help debug? All right. Add those 2 lines. Oh, why did I close Visual Studio? That was dumb. I thought I was closing the editor. So that's a structure. I'm going to probably try to use a structure each time we have another class period, just to start burning it into your brain. Although after our next structure, we'll start using classes exclusively, because a class is exactly the same thing as a structure, it just has functions added in. And if you have learned enough about Python, you may have seen classes in Python. But they're actually a little bit more convoluted in Python, which is weird because the syntax for Python is simpler, right, usually. But defining classes in Python is a little bit weird. So let's talk about pointers again. What is a pointer? I'm going to type some notes here, and you don't have to type them in because they're going to just kind of be, I wouldn't recommend you bother typing. But say you add a memory block, you know, and since ints are, 4 bytes long, your memory block might look like this. That's quite enough. And so your code does this: int x, y, and z. Well, what happens? This x is actually going to be stored at memory address 1000. And this variable y is a new name for that memory address. And this variable z is a new name for that address. So if we do this, x equals 3, what does it do? Well, at this point, x is at memory address 1000, y is at memory address 104, and z is at memory address 1008. Now, we don't know that. The compiler's picking all that, and when it runs, at runtime, it picks all that. But when we say x is equal to 3, it goes and it looks, oh, what memory address is x, a nickname for? X is a nickname for address 1000. So it runs up here and it stores a 3. There. And then we say y is equal to 4. All right, well, 4 is a nickname for memory address 1004, so it comes and puts a 4 there. And then when we say z is equal to x plus y, what does it do? Well, x is a nickname for 1000, so it gets 3, and y is a nickname for 1004, so it gets a 4, and it adds those together. That 3 and that 4 is equal to 7. And that 7 gets copied into z, and z is a nickname for 1008. All right, now that works great. And in many languages, that's as far as you can take it. A lot of languages won't even tell you what those memory addresses are. You have no way of finding out where A is stored, or where B is stored, or where X is stored, or where Y is stored. But we do in this language. You can use what's known as a pointer, and the pointer syntax is like this: int p. And you don't have to put the p there, but a lot of people, it's the industry standard that all your pointers begin with a p. So int px, int star py. The star means that it's not a variable, it's a pointer to a variable. And int star pz. And then if we do this, px equals ampersand of x, and py is equal to ampersand y. This ampersand means address. So, if x is a nickname for 1000, when we say px is equal to ampersand x, it doesn't run up here, find 1000, and store 3 in that variable. Instead, it actually stores that memory address itself, not the data it's containing. So px is equal to 1000 at that point. And then when we say py is equal to the address of y, well, what is the address of y? According to my little notes here, somebody tell me. Y is a nickname for what address? 1004. Yeah, 1004. So at this point, the pointer of y contains the value 1004. So a pointer doesn't hold the data. It holds the memory address where the data is stored. And we wound up not using 1012 and 1016, so I'm going to delete those. All right, let's do that in our code. Right above system pause, return 0, and if you're not using system pause, you know where to put it anyways. Int x equals 3, int y equals 4. Now let's declare 2 pointers. Int star, the star means it's a pointer, px semicolon, int star py semicolon, and then px equals ampersand x. Give me the address of x. Give me the address that x is a nickname for, that x is a pointer to. And then py equals ampersand y, semicolon. And let's print those things out. Let's see out, arrow, arrow, px, arrow, arrow, space, quote, excuse me, quote, space, quote, less than, x, less than, e and dl. It do the same thing for y, so you may as well just copy and paste that line. Alrighty. Now when I run it, I'm going to find out what memory address these variables are stored in. Or not. I'd already defined something called x. My mistake. I don't know where. But somewhere up here I have a variable called x. Well, what do you know? Okay, fine. Phooey. There, that solves that. So now when I run it, there's my code. If you get an error, if you take out the int, then it's because you've commented out the line x equals something up above. So you may need to leave that int there. You'll know if you compile it and it doesn't work, which way to go. All right, here we go. That is the, let's zoom in the font. That is a memory address that x is stored at. And that's the memory address that y is stored at. Notice they're not even close. It's kind of weird, but it picks what memory address is stored in. And those are like 300 bytes apart from each other. So it's weird that they're not what's known as contiguous, one after the other. But it doesn't matter usually, right? We don't get to pick them. We don't even usually need to know. Alrighty, now that we have pointers to these pieces of data, we can change those pieces of data without even having the original variable. What do I mean by that? What if I wanted to set y equal to 100, but I didn't want to use the y variable for some reason? I could use the pointer. And here's how I would do that. I would say star py equals 1,000 or 100 or whatever I said I was going to change it to. What this syntax means is that whatever memory location is stored in py, go there and change it to 1,000. Just like in my notes over here, if I said asterisk py equals 123, what it would do is at this point py contains 1004, and so it would run out to the address of 1004 and write 123 in it. So it would run out here, it would find 1004, and it would put 123 there. This is called dereferencing. Not really sure why. I'd have to look it up. This is called let's put that actually in our code. Go back over here. This syntax is known as, quote, dereferencing a pointer. It takes the memory address that is contained within that pointer and then goes and accesses what's at that memory address. Now, if we write out py at this point, or no, just write out y. Cout less than y equals, end quote, less than y less than ENDL. The last we saw, it equaled 4. But after this, it's going to equal something different. Now it equals 1,000. So without a line of code even referencing y, nowhere did we have y equals anything. But by using its address, we were able to change it. Just like if I gave you my home address, you could drive by my home and paint it red, right? Well, here I have the address, and so I can go and I can set it to 1,000. The computer can anyways, without having the original piece of data. It doesn't have that original variable. We're not accessing it. Yeah, we could, right? We just did here, but we didn't change it through it. We changed it through its pointer. Now here's how you can blow up your program or cause an error. What if you changed the value of py? It's a memory address, right? So what if you say py is equal to 12? Well, hopefully it's even giving me an error. Yeah, okay, good. It's giving me an error. It's not going to let me do that. All right, so we're not going to concentrate on that right now. So that is a pointer. And then there is one more thing called a reference. A reference is when you have two variables that point to the same piece of data, or that are the same piece of data, that are the same address. Let's make a reference to x, but we're going to give it a new name. So int ampersand x, no, needs to be a new name, z. And then z is equal to x. I seem to be making a mistake here, so I'm going to bail out of this discussion pretty fast. Why are you complaining? Oh, it requires an initializer. All right. So int ampersand z equals x. Okay, so now z and x are the exact same thing. So if I say z equals 9,000, and then I cout x, it's going to print out that x is 9,000. Because z and x are now the same variable, even though they have two names. You know, I have two names. People call me Professor Thompson. People call me Jeff, right? So if you go and you throw Jeff off a building, you're also throwing Professor Thompson off the building. It's one person with two names. Here we have two variables, two variable names pointing to the same data. So that's what a reference is. And a reference is a little bit different than a pointer, because notice we didn't have to use that star, right? And we did not have to, you know, retrieve the memory address with that. But, you know, now we're using ampersand in a different context, and it sure seems like we got a whole bunch of ampersands in a whole bunch of different places. You just have to learn it. If you're trying to get the address of something, you put it in front of the variable. If you're declaring a reference, you put it in front of the variable being declared. One or the other. So z is a reference to x, which means that z and x are now the same variable. And changing one automatically changes the other. That doesn't even make sense to say. It's like I have two signs pointing to my house. And then I follow one sign and I paint my house green. Well, the other sign's now also pointing to a green house. And so I don't even know how to word that. And changing one automatically changes the other? That's not exactly quite right. Just that z and x are now the same variable. Changes in z are reflected in x and vice versa. Is that a good enough way to say it? I think so. Because of the same thing, they just have two different names. Two different signs pointing to the same street. It's the same street, even though you see two street signs for it. Alrighty. So now we have discussed structures, pointers, and references, and prototypes. Okay. What are we going to do next? We're going to go and create our structure and our prototype and put it inside a header file. So we need to go and create a header file. So we're just going to go back to our Solution Explorer, View, Solution Explorer. You didn't close yours like I did. Right-click on Source Files and do Add New Item. But instead of a C++ file, choose Header File. And what is our structure going to be? It's going to be a point that has an X and a Y coordinate. Maybe an X and a Y and a Z coordinate. Just X and Y. So point.h. I capitalized it just for funsies. Add. Alright, ignore the fact that there's this interesting little piece of preprocessor definition there, and let's write our new structure. Structure space capital P point. Excuse me, it's not structure though, it's just struct. Struct space point. Open curly brace, and it's got two pieces of data, int x and int y. And now we're going to write a function, I don't know, print point. But we're not going to put the function inside the header file. That's kind of bad taste. So I'm going to go back over to, anybody still need this, or are you good to go? You need me to slow down, that's cool. Alright, I'm going to go back to source files and add a new C file. We'll learn what adding a C++ class does. And create it and call it point.cpp. The other one should have been called point.h because it's a header file. If this one's not called point.h, you've already got a problem and this next step's not going to work. Alright. Now this one needs to include the header file. So # include. Now we have been putting all of our includes inside of angles, but this CPP file is, this header file is in the same directory, so we don't use the double angles. Instead we put double quotes around it. Point.h. And I'm capitalizing it exactly the same capitalization as my actual file name. And I hit Control S and my red underline for the error disappeared. Alright, I'm going to write a print function for the point, just like I did the other time. Void print underscore point, and it's going to take a point as a parameter. So capital P point, just P. Is that good enough? I think so. Close parentheses. And then so we're going to see out something, but to see out something we need to have standard I/O included, and we have to do using namespace. So we have a couple more includes we need. Include angle std I/O. Wait, no, it's I/O stream. I'm spacing out. I just taught a C class an hour ago. I/O stream. Include less than I/O stream greater than. and then pound, or no pound, using namespace std. All right, so now I'm going to see out the word point, space x equals, space end quote, arrow, arrow, x, arrow, arrow, quote, comma, space, end quote, semicolon. And now let's print out its y coordinate. Oh, look at that, I made a mistake. It's not x. Where is x? X is nowhere defined. X is part of p, so I need to put p dot x there. Now I'm going to do the same thing for y. I could just copy and paste it, but I'm going to type it in again. C out less than, quote, y equals, space, end quote, less than, p dot y, less than, ENDL. So now I have a print function. Just like we had a print for the employee, we have a print function for the point. Great. As soon as y'all are done typing, we're going to go back to main and we're going to create a pointer 2 or 3. So this lecture actually has a point. Uproarious laughter now, please. Thanks. Okay. So, are we good? Can I toggle back to main, or you need no? A little bit more typing time. It should at least compile at this point. So make sure it compiles. Build, rebuild solution. I don't want to see any errors. Good. One succeeded. Yes, sir.
What was the point H again?
In capital P point H looks like this.
Oh, it's just the structure.
Yep. With this line here. Pragma once. It added that when we created it. I'll tell you what that means in a few minutes. All right, let's go to main, which is inside lecture 1, and add a few points. So right above our system pause, or right above our return statement, I'm going to create some points. Point space P1, comma P2, semicolon. And it doesn't know what a point is. Why? Because a point structure is declared in point.h. So we got to go and add a # include for that. It has to know what a point is. And again, since it's in the same directory, we're not going to use the angles, we're going to use quotes. So # include quote point.h, end quote. And then just hit Control Save or Command Save to save it. There, now that line is no longer a syntax error because it knows what a point is. And we can set the values. P1.x equals something and P1.y equals something. P1x equals 1, 2, 3. P1.y equals 4, 5, 6. P2.x equals -2, -1. P2.y equals -20. Whatever, -10. Who cares? Now I want to let's run it and make sure our syntax is good. It's always good to take, itty bitty little steps. Make sure we haven't broken the code. And again, this is right above our system pause. Didn't mean to hide where we were so well. Alright, it compiles with no syntax errors. Good. Now let's call our print function. Print underscore. Now, I don't remember its name. I better go look. What's it called in point.cpp? It's called print underscore point. And apparently I didn't capitalize anything there. So I need to remember that. Come back over here. Print underscore point, parentheses, P1, in parentheses, semicolon. Print underscore point. Uh-oh. I can tell I'm in trouble already. P2, parentheses, semicolon. So what is wrong? based on what we had to do to fix it when print employee was at the bottom of the code. What did we do to fix it? We made a change above main in order to fix it so that it knew what print employee was. You remember what we did? The prototype, yeah. So we need a prototype for print underscore point. Let's go do that. Now this is absolutely the wrong place to put it, but it would fix it. Putting it here would fix it, but it's not where we want it to be. We want it to be inside the point class so that everything that includes, point structure, so that everything that includes point.h also has the print function. So I'm going to go back to the header, point.h, and I'm going to write its prototype there. The easiest way of making a prototype is just to go and find your header and copy and paste it and put a semicolon at the end. So I went to point.cpp. I'm going to copy my header. I'm going to go to the H file, point.h, and I'm going to paste it. And now main understands what that function is. What did it need to understand about it? Why is it having to bother doing this? Because it needs to know what kind of data it accepts and what kind of data it returns before it can compile it, before it can, like, dig the holes necessary in the concrete, to put the beams inside. It has to know the specifications. That's why we bother to create prototypes, is to tell the compiler what specifications there are. Now in newer languages, like Java, you don't have to declare prototypes. It figures it out as it's compiling it, but we sure do in this language. Alrighty, I'm going to Control S on my main. I'm going to Control S on the point.h. I'm going to Control S or Command S on your editor or whatever on point.cpp. I'm going to go back to main and try to run my code. See if it works. I want to go back down to where my pause statement is, because these are my newest lines of code here. Alright, and it printed out our 2 points. X equals 1, 2, 3, y equals 4, 5, 6, and x equals -1 and y is equal to -10. Is it working for everybody? If not, let me get my eyeballs on your screen. So if you're getting an error on these 2 lines, it's probably because you didn't successfully add the prototype in the right place. You're going to go to point.h and put it there. And the easiest way of doing it is just to copy the header of the function here and go back to point.h and paste it and add a semicolon. Like that. It would be an interesting assignment. We did do that calories program, right? Did we do a calories program where you had to, it would tell you that you better eat 1,600 calories a day? Is that sounding like a big no?
This class.
Okay, you did it in Python, but not this one. Okay. Well, then I won't use it as an example. Maybe I'll change it to use structures. Okay. Back to the PowerPoint. Why don't we take a break? Come back in about 5 minutes. All right, back to the PowerPoint. Loops, logic for keeping a running total. That's what we talked about last time. It's just where you create a variable and then inside the loop you update the variable. I think I'm going to leave that example alone. So sentinels. A sentinel is just a value that stops the program. It better be a value that cannot be confused with a valid test value. Like if you decide that your test data entry for grading exams will stop as soon as the user enters a special value, and then you make that special value 55 for some reason. 55 is a bad idea if 55 is a valid test score. Somebody might make a 55, so it would be a very bad sentinel value. So instead you pick something that cannot be confused with valid data, like -999, something like that. I just like using -1 if it's a test score because nobody can make below a 0 on my tests. And you use it to terminate indefinite loops when you don't know how many things you're going to process. You don't know how many test scores, right? Or you don't know how many pieces of data you're going to read. So something like this. Let's write a program that asks for test scores and adds them to a total. And I want to do that inside main. And so I'm going to go back and find my main, and right above the system pause inside of main, let's go ahead and declare our variables. I'm going to create something to hold the sum total of all of our scores, and I like making my sum totals doubles, just so that they're a floating point type, so that if we calculate average, it already is a floating point type and we don't have to worry about integer division. So double total is equal to 0. And we may as well create our test score variable as well, double score. We don't even have to initialize it because the user is going to fill it in. Maybe we should, though. Now let's ask the user for a test score and let them type it in. So cout less than quote enter score or -1 to quit in parentheses space colon end quote semicolon. And you know dang well what the next line of code is going to be. CIN greater than score. And then we're going to have our while loop so that it'll keep repeating. While parentheses, while parentheses score not equal -1. We're going to add that score to the total. Like total equals total plus score. Or the shorthand for that, total plus equals score. And now we better get another score. So we're going to do these two things again. We could just copy and paste them. If you feel like typing them, if you're a masochist, go for it. But I'm going to make it say enter another score, just to be a little bit different. Enter another score, -1 to quit. Alrighty. Let's go and print out the total after they've typed in a -1. So once it exits the loop, cout less than quote total of all scores equals space end quote less than total less than ENDL. What if we put that in the wrong place? What if we put that above the curly brace? It wouldn't be a disaster. I'm going to cut it and move it above the curly brace. You don't have to do that because I'm going to move it right back in a minute. I just want you to see what happens. I wish I could make these line numbers smaller. Right? It's not like they need to take up a quarter of my screen, but whatever. And so when I run it, it's going to ask for a test score. Right? Enter score 100. And it says enter another score 200, and it prints out the total. Total of all scores is 100. Well, it's not 200 yet. All right. It's just not behaving the way we expect it to. And the reason why is because I made a mistake and I put something inside the body of the loop that should be outside the body of the loop. I don't need to print the total until the loop is entirely done and we have all of our totals added up. So I'm going to put that back where it should have been. And now it's going to be better behaved. That's a common programming mistake, putting something inside the loop that should be outside of the loop or vice versa. All right, so 100, 90, 80, -1. And so the total is 270. That's a running tally. What this called running total. And it uses a sentinel value. It uses that -1 as a special value that cannot be confused with a valid value and terminates the input. All right, suppose we wanted to calculate the average, though. We need to know a little bit more information about an average, because what is an average? It's the total divided by what? If you want to know the average height of all the kids in your class, you add up all their heights, and what do you divide it by? The number of kids. So we need a counter that keeps track of the number of scores. And since it's a whole number only, right, we could declare it as an int. So up here, after in my declarations up here, I'm going to do int num underscore scores equals 0. We don't have any scores yet. But if they type in a good score and it goes inside the while loop, we certainly have a score now. So num underscore scores plus equals 1, semicolon. And then after the curly brace, why don't we print out the number of scores, and then the total of the scores, and then the average. So maybe above the total of all scores, cout less than quote, number of scores space equals space end quote less than num underscore scores less than ENDL. And how do we calculate the average? This is total divided by the number. So let's make a variable to hold that. Double space average equals total slash forward slash under the question mark total divided by num underscore scores. And let's print that out. Cout less than quote average. I guess technically it's called the mean. You know what? I never really understood exactly what the difference between the average and the mean was. All right. Average equals end quote. Here I'm betraying my lack of math major status. Less than average less than ENDL. All right, inner scores, 100, 90, 80, -1 to quit. There's 3 test scores. The total is 270, and so the average is 90, which is what you'd expect from 100, 90, and 80. All right, this code can lead to a runtime error, maybe. Or if it's not a runtime error, it's going to at least produce some output that you wouldn't expect. What happens if you don't enter any test scores at all? What is num scores going to be if we don't enter a single valid score? If we type in -1 straight from the beginning, then num scores equals what? I'll highlight it. If we type in -1 from the very beginning, then it doesn't even go into the while loop. So num score stays 0. So when we get down here, what are we doing? We're dividing by 0, which might cause an exception, which might cause a runtime error and kill the program. In this case, I don't think it's going to go to, because that's what happens if you have an int divided by an int. But if you have a double divided by an int, it doesn't crash it. It just produces some really weird looking output. So if I type in -1 from the get-go, it says average is equal to -nan parentheses IND, which is nothing that a teacher wants to see when they're trying to grade their grades. What does that stand for? Not a number. Some other languages would use the word infinity, right? Something divided by 0 is infinity. You may have heard that. So it's not too cool to print out something weird like that. So what we ought to do, and I'm not going to do it because it'll make our code a little bit more complicated, is that if the number of scores is 0, we shouldn't even try to print the average, right? So we ought to have an if statement. I guess it wouldn't take too long to do it, right? If, parentheses, num underscore scores greater than 0, in parentheses, semicolon, get rid of that close, parentheses, close curly brace, and put these things in here. We don't want to calculate the average unless they actually typed in a valid test score. We're just making the program a little bit better there. And if we had made the test scores and the total integers, then it would actually crash the program, because an integer divided by 0 is a program crash. It's not just equal to that NaN parentheses IND thing. So -1, number of scores 0, total of all scores 0. Now the way our brains work, if you asked me the average test score and I didn't have any test scores, I might say 0, right? But that's technically not true. You don't have an average if you don't have any pieces of data. It's like asking what the average weight of the elephants in the zoo is if you don't have any elephants. There's no average. So that's why we're doing that. Does anybody need syntax error help? Are we all good? Think we're all good? All right. So deciding what loop to use. While loops are pretest loops. They iterate as long as a certain condition exists. They can be used for validating input. They can be used to reading lists of data terminated by a sentinel. That's all valid. That's all true. The do loop is a conditional post-test loop. It always iterates at least once. They say it's good for repeating a menu. I guess I'll buy that. And then the for loop is a pretest loop with built-in expressions for initializing, testing, and updating, and situations where the exact number of iterations are known. I'll give you a slightly different definition for when I think you ought to use these loops. Maybe I'll just tack them on right here. Maybe I'll open a multi-line comment right here. Use a do loop if the body of the loop must execute at least once. If you don't want it to ever not let you into the body. Like, it was okay to not go in here if they typed in a -1, right? We didn't need to add it to the total if they typed in a -1. So we used a while loop. But if we needed to go into the body of it anyways, we might make it a do loop. So you use a do loop if the body of the loop must execute at least once. Next, use a for loop to step through a series of values, like a counter-based loop. Oh, I love that. Whenever I say the word series, my phone thinks I said Siri, and it starts listening to me. Stop that. I like doing that in class. Hey Siri, blah, blah, blah. And see whose phone starts listening. Or hey Google. All right, and then lastly, otherwise use a while loop. Those are my recommendations rather than what they say. They say kind of the same thing, but I think my way of saying it is more succinct. We're almost at the end of loops, but I think that it goes off on a tangent almost as weird as what we did, which is files. Oh, nested loops. Got to do nested loops. We already know what nested if statements are. Nested loop is a loop inside of a loop. Like, what if you wanted to write a clock that would print out every 15 minutes between the hours of 1 and 7, something like that, 1 through 6. So we wanted to print 1, 115, 130, 145, 2, 215, 230, 245, and so on. Well, let's do that with while loops. Excuse me, for loops, because I think for loops are more efficient. We use a for loop to step through a series of values. It's a counter-based loop. So for, parentheses, int hours equals 1, we're starting at 1 o'clock, semicolon. We're going to keep going as long as hours is less than or equal to 6. Hours less than equals 6, semicolon. Hours plus plus, we're only going to go up, 1 hour each time, in parentheses, open curly brace. Now let's do the same thing for minutes, except we're going to start our minutes at 0 and go until they're less than or equal to 45. So to count out 0, 15, 30, and 45 each time, and we're going to add 15 to it each time. So for, parentheses, int minutes equals 0, semicolon, minutes less than 45. And why not 60? Because I don't want it to print 1:60, right? That's not a valid time. Or 2:60. I guess I could make it less than or equal to 59, though, because there's, your minutes can go from 0 to 59. Just a sec. Semicolon, minutes plus equals 15, because I want to print every 15 minutes. Yes, sir.
Couldn't you do just less than 60?
I could do less than 60, exactly. Perfect. They mean the same thing, less than or equal to 59, but less than 60. My brain actually likes that, so good suggestion. And that way, if I change it to print every 5 minutes or 1 minute, it's still going to work. Okay. Now, inside the nested loop, the inner loop, we're going to see out less than, quote, hour equals, end quote, less than hours, less than, quote, space, minute equals, end quote, less than minutes. I'm going to go to the next line because, I guess there's almost enough room. Yeah, I am going to go to the next line. Less than, ENDL. And obviously, you don't have to go to the next line. All right, now when we run it, we're going to see a count from 1 o'clock to 6:45. -1 because I don't want to enter test scores, and we can see it working. 1, 0, 115, 130, 145, 20, 215, 230, 245, and so on. Now, if we were awesome, we could try to make it say 1:00 and 1:15 and 1:30 and 45 and so on, but we'd have to do a little bit of fancy formatting to make sure that it printed 2 digits even if it was a 0. So I'm going to leave that alone because that's not the point of the assignment. The point of the assignment is to understand nested loops. Let's do another nested loop. I want to print a multiplication table. And don't type this part because I'm going to delete this. But I want it to look like this. I want it to multiply all the numbers between 1 and 5. Right? And this place is going to equal 2 by 2, which is 4. And this place is going to equal 3 by 2, which is 6. And this one's also going to equal 3 by 2, which is 6. And 4 and 2 is an 8. And a 5 and a 2 is a 10. Right? A 4 and a 2 is an 8. You know what a multiplication table is. I don't need to. Okay. I'm not going to fill in the rest of it. I'd rather code it. So what is this going to be? We're going to have an inner loop that prints out all the columns. And the outer loop that goes down and starts a new row. So the outer loop is going to be row, and the inner loop is going to be column. For, parentheses, int row equals 1, semicolon, row less than equal 5, semicolon. I mean, we could go out to 10 or 9 or whatever. Row plus plus, close parentheses. curly brace. Same thing, except I need a variable called column. I'm going to abbreviate it COL. 4 parentheses int call equals 1, semicolon. Call less than equal to 5, semicolon. Call plus plus. And I'm going to put in an intentional logical error just to demonstrate something, but we'll fix it. So open curly brace, and let's print out row times column. So C out less than row times call less than quote backslash T, or we could use IO manipulators in order to format the data better than using tabs, but yeah, I'll just leave that alone. Semicolon. Now let's run it and see what it looks like. And as I said, there's definitely an error with it. It's not going to look like a table. -1. All right, what's wrong with my table here? 1, 2, 3, 4, 2, 4, 6, 8, 10, 3, 6. All right. What are we doing wrong? Where should the next row begin? After the 5, right? It ought to print out 1, 2, 3, 4, 5, go to the next row. 2, 4, 6, 8, 10, go to the next row. 3, 6, 9, whatever. So, to get that to happen, I need to add an extra print statement, a print ENDL. And that needs to be outside the inner loop, because the inner loop is the one that's printing out all the columns. It prints out 1, 2, 3, 4, 5. And once the inner loop is done, that's where I want to print my ENDL. C out less than ENDL. Now it's going to look a whole lot prettier. Yep, there's our multiplication table. So things to note about nested loops is that the inner loop has to repeat all the way through and finish all of its iterations before the outer loop can iterate one more time, right? So it prints out all the numbers here before that inner loop is done, and it hits the ENDL and it starts a new row. Just like our minutes, right? Our minutes have to increment all the way through until the inner loop is done before the hour increases by 1. And it keeps doing that until both the minutes is done and hours condition is done. And so it falls out of the outer loop. Any typing time needed? We all good? All right. So the inner loop goes through all the repetitions before any repetition of the outer loop, right? It printed out all the numbers in a single row before it did the ENDL and then reiterated the outer loop. So that means that the inner loop repetitions complete sooner than the outer loop, right? When we ran it, it printed out all of the minutes, 0, 15, 30, and 45, that finished before the outer loop iterated one more time. And how many times did this thing iterate total? How many times did we print out a row times a column? Well, if we run it, it'll be real obvious. How many total numbers did we print out in this block?
25.
Yeah, 25. The number of iterations of the outer loop multiplied by the number of iterations of the inner loop is the total number of times that the body inside the inner loop was executed. So I guess I feel like adding those as notes here. Slash less than. The inner loop must complete all of its iterations before the outer loop can repeat one time. And the inner loop body repeats How am I going to word this? Or the, okay, yeah, I'll word it like that. Back space over that. The total number of iterations of the body of the inner loop is the iterations of inner loop multiplied by iterations of outer loop. So in our multiplication table, outer loop or inner loop repeated 5 times equals 5 iterations. Outer loop equals 5 iterations. So total numbers printed. So total numbers printed was 5 times 5 equals 25. Now how about our clock? Well, we started with 1 and we ended at 6, so 1, 2, 3, 4, 5, 6, 6 iterations. And then how many minutes did we count in each hour? 4, right? 0, 15, 30, and 45. So the total number of things we printed was 24. 6 hours times 4 divisions per hour. And if I ran it, I could count them. I'm not going to count them. I'm not that obsessive. But, right, if we looked, since each one is divided up into 4 sections, each hour is divided up into 4 sections, and we have 6 hours, 6 times 4 is 24. 5 rows, 5 columns, 25. Using files for data storage. Now this is just totally different. It ought to be its own chapter. I almost feel like saying we're done, except then when you hit the quiz, and it's going to ask some stuff about files, so we have to cover it now. Alrighty, we'll do it. But for now, we're just going to do an example of it. And then we may end early. Okay, so to do files, the way that a file works is that if we had a file open, say it was called F1, and we wanted to write to it, don't type this. Doing that would write to the file, just like cout writes to the screen. You can save to a file using the same syntax. So your syntax is to open the file, to use it, you know, read from it or write to it or both, and then close the file. And what do? You use your files instead of the keyboard for input, and you use your files rather than the screen for output. And why do you do that? So you can save your data. It'd be really annoying if you had to type in a term paper and then the next time you needed to print it out, you had to type it in again, right? You want to save it to disk and then load it in later so you can print it in again, print it out again. So there is a header called fstream, file stream. Just like iostream, we use iostream for cout and cin, right? Instead, we're going to use fstream. And we have 3 different types, 2 of which we're going to use. ifstream stands for input stream. ofstream stands for output stream. Well, we're going to save to a file. So let's use an ofstream. But we're going to have to go up and include #fstream up at the top of our program above main. So that's going to be the first thing I do, is scroll up to the top. I could put it below or above point H, it doesn't matter, but I'm going to put it above it. #include less than fstream, file stream, greater than. And I'm going to put as a comment here for file IO. Then I'm going to scroll back down, and maybe I'll copy and paste that multiplication table and I'll write it out to a file instead. But we have to open the file first. So we're going to need an fstream variable to open our file. and it's an output stream, so it's going to be OF stream space F out. Rather than C out for console out, how about F out for file output? Now I'm going to toggle back to the PowerPoint because I don't want to make a mistake here. We use the .open command, method. Notice that it's attached to our variable. A function that's attached to a variable like this, like .open, is called a method. It's just a function that's attached to a variable, and you define those inside classes. So we'll do that next time. So let's do it. fout.open space quote. And what am I going to call this? I'm just going to call it table.txt, right? Because it's a multiplication table. Table.txt. And why am I calling it .txt? So it'd be a text file, and I can open it with Notepad or whatever editor I have declared to open text files. You could call it anything you wanted, right? You could call it, you know, DianaRoss.mp3, but that'd be kind of stupid. Alrighty, let's copy this table, this multiplication table. This was a 5 by 5 multiplication table. Let's just go up here and copy it. Both the inner and outer loops. Copy it. Come down here, paste it. Right there, but change the C outs to F outs. And when you're done writing to a file or reading from the file, you want to close it. Because you've probably seen that before. You try to save a file and it says file is open somewhere else, right? Another application has the file open. Or you're trying to copy it to another disk and it says that it can't copy it because the file is open. Well, you want to close the file as soon as possible. And so as soon as the multiplication table is done, I want to close the file. fout.close, parentheses in, parentheses, semicolon. Now this is not perfect code because it's not fail-safe. If I try to write to a drive that's full, or to a drive letter that doesn't exist, it doesn't handle that error condition. But it's enough to prove the point that writing to a file is as easy as writing to the screen. All I had to do is add in a couple of extra words. I had to create a file handle. A file handle is the term that people use for the file variable. You had to create the file handle, you had to open it, and then you had to close it at the end. And then the rest of it was just, using fout rather than cout. What if we didn't want to call it fout? We could just call it file, for example. I'm going to undo this, right? And as long as I use that word consistently through it, because there's nothing magical about fout. It's just a variable that I chose to make it easy to change from cout to fout. But that would compile just as well. Okay, let's run it. -1. All right. Now, I didn't put a print statement to say that the file was saved to. So the user doesn't know that we created a file. But it's there. If I go look in the place where my program is, my program project is, wherever you go and you get your CPP file, go there. Mine is in Documents, Lecture J, Lecture J, and I'm not seeing it. Well, I'll find it another way. I'm going to open my Solution Explorer, right-click on the top line that says Solution Explorer Lecture J, do Open Folder in File Explorer, and my text file should be right there. And it's not. Well, why do you know? What am I doing wrong? You don't know. Is it in the debug directory? Nope. Oh, it's there. I didn't spot it before. You should have a file called table. And I didn't spot it because I've disabled file extensions. I'm going to re-enable file extensions. Excuse me while I do that. All right. So if I got into Documents, Lecture J, like normal, right? Documents or wherever you stored in your Visual Studio directory or whatever, Lecture J where the source code is, we'll see table.txt, or maybe it's just called table. And if you double click on it, you see our multiplication table. That's how easy it is to save to a file. Is that working for everybody? Did everybody get the file open in Notepad who wanted to?
I got the file, but it doesn't have any content.
No data in it. That's interesting. Let's go and look. Oh, change these couts to couts. No, because that's how it winds up actually getting into the file. Well, that's interesting. We'll rebuild and build. So I don't know why I didn't want to. So I'm going to just try and open space. Okay, good. Thanks. Going for y'all? Good. Now what if we wanted to do something with this file, like bring it in to Excel? So you could do it with a spreadsheet. So you could work with it as a spreadsheet. We might want to change the format of it a little bit. Actually, we don't need to because it's already separated by tabs. And you don't have to do this, but I'd like for you to watch if you're not gonna. I'm going to launch Excel, and I'm going to open it as a text file and tell it that it's a tab delimited file. Delimited just means that every piece of data is separated by a tab. So I'm launching Excel. I'm going to come over here and do File Open. And it's asking me where. So, okay, this PC. And I sure do just like how it presents this. All right, Lecture J, Lecture J. But it doesn't know because it's not a .xl file, so I need to tell it to open text files. It's not leaping out at me, so I'm just going to tell open all files. So, oh, there it is, text files. And there's table.txt. And I'm going to double click on it, and it asks some questions first. It asks me, this says text import wizard. Is this a delimited file or a fixed width? Fixed width would be like if every number occupied 5 spaces on the screen. Well, it's kind of true, but that's because we separated them with commas. Excuse me, tabs. So it is a delimited file. So I'm going to choose delimited. I'm going to click next, and it's delimited by tabs. And you notice when I select the tabs checkbox, it's starting to look like a spreadsheet. And I click next, and I'm just going to say that all of this is general format. I'm not going to do anything else. And there's my data. I could draw graphs with it or whatever. So if you're ever doing a project and you want to print some, display some output on the screen, but then you want to make a fancy graph out of it, you can do that. Save it to a file, make it a text file, and then go into Excel and open it as a tab delimited file or comma delimited file, however you wrote the data out, and then you can start doing stuff with it. So if you were going to read in the file, instead of OF stream, you'd use IF stream. But we're going to stop here. I know it's a little bit early, but we've covered a lot of stuff actually. structures and pointers and references and loops and summation loops and nested loops and now file I/O. I think that's enough for one lecture. We only have a little bit left to do, actually. It may look like a lot of slides, but it's not. One more thing you might want to do is let the user pick the file name to save to. You might ask them, what file name? Rather than always going to table.txt, we might ask them. And then breaking and continuing a loop. That's what we're talking about. We're not done yet. If you've already closed Visual Studio, fine. But here's what break means. We've used break when we did switch and case, right? Have we done switch and case?
Yeah.
Yeah, okay. So we use break for that. We're going to use a break in a loop. So one more loop down here at the system pause. I don't know. I'm just going to put the numbers from 25 to 35 for whatever reason. For parentheses int I equals 25 semicolon I less than or equal to 35 semicolon I plus plus curly brace. I'm going to print out I, so C out less than quote I equals end quote less than I less than ENDO. But I'm going to do a special check. For some reason, I hate the number 29 so badly that I want to quit the loop when it hits 29. Now realistically, I just changed this, but just pretend with me. If parentheses I equals 29, close parentheses, open curly brace, C out, oops, 29, let's break, \n, in quote semicolon. And then after that, put our break. Now it's not going to count from 25 to 35. It's going to count 25 up to 29, and then it's going to hit that. It's going to print that out, and it's going to break out of the loop. And like I said, this is a dumb usage. If I really wanted to count to 29, I would do this. But there are times when you actually want to break from a loop early, like a sentinel loop, right? If the user types in -1, if input equals -1, break. Or if an error condition arises, right? The disk fills up, you want to bail out of the loop so that you stop trying to write to the disk. Let's run it, and we'll see it count. Oops, 29, let's break. All right. Now we're going to mess with this even a little bit more. I don't want it to stop at 29. I want it to go a little bit further, so I'm going to make that a 31 or 32, whatever. But I'm going to put something else up here. I'm going to say that if the number is equal to 27, we're just going to continue. And what continue means is don't do the rest of the loop. Just come right back up to the top and increment 1. So if parentheses I equals 27, that's not supposed to be minus, equals 27 in parentheses, open curly, then C out less than I despise 27, \n, end quote, semicolon. Continue. Semicolon. So it's not going to even get to print it out. A continue is just like a break statement, but the break statement causes it to go to the close curly. Continue causes it to go back to the top and increment I and go on its and start working again. So it's not going to ever print out this thing for 27. So we see what it's doing, 25, 26. I despise 27. So it didn't actually print out I is equal to 27 because the continue stopped it before it hit that code. It jumped back up to the top. Then it kept going, 28, 29. And when it hit 29, it got to this statement, and the if statement was true, so it broke out of it, broke out of the loop. Now, I actually don't use continue very often, but it can be useful. But break, I used an awful lot. Alrighty, I think that is enough, especially because I'm losing my voice. Does that make sense? Pretty good? Okay. So we'll make a Dropbox and we'll upload it. We do need some homework. We're going to have actually, unfortunately, 2 pieces of homework, but they're not hard assignments. Well, we may not have to if I can't find it instantly. Phooey. Pause the recording. Y'all don't need to see while I... Or not. Alrighty. So, you can write some loops. You're going to write a while loop that prints all the numbers between 1 and 100. You're going to write another loop that prints the numbers between 100 and 1000, skipping 50 each time. So, you'll probably just do counter plus equals 50, something like that. Or if your variable's I plus equals 50. And then write a for loop that prints all the numbers between 1001 and 1020 by 1. And write a while loop that counts from 20 down to 1. So you're going to use, minus minus rather than x. And then lastly, you're going to rewrite loop B using a do loop rather than a while loop. It's going to work the same way. You're just going to have to copy and paste and change a couple of lines of code, move things around to get that to work. But that ought to be enough to prove that we know how to do loops. That makes sense, gang? All right. And let's make ourselves a Dropbox.